In this video we're going to define impulse, and then we'll relate impulse to momentum. Okay, we also look at something called the impulse momentum theorem. But let's first begin by defining impulse. Impulse itself is defined, it's denoted by the symbol I, and it is equal to the force multiplied by the time. Now this definition can be used only when F is constant. So if F is constant, then you can use this. And if F changes, then we need to tweak it a little bit, and we do what we do in all cases. Anytime you're dealing with products, and if F changes, and if say F is given as a function of time, the force itself is given as a function of time, then you can find the impulse. Let's say if it's given something like this, with this curve, and between time t1 and t2, if you're interested in finding the impulse, all you do is you find the area enclosed by the curve within those limits, and with the appropriate limits of time. So to find impulse for variable forces, okay, so if F changes, then I can be found by calculating the area under the curve. Now in the C class, basically what we'll do is we'll use integrals, and it'll be from between some time t1 and t2, f of t multiplied by t. So this is a simple transition. For the ones in the B class, all you need to worry about is that it is either f times delta t if f is constant, and it is equal to the area under the curve if f changes. So those are the two ways of finding impulse. Now let's apply these very quickly to a couple of simple examples. And so let's say that let's look at the one with an area. So let's say that there is you're given the graph of force versus time, and let's say that the value of force is 100 newtons. The time is 1 second here, it's 2 seconds, and it's 3 seconds. Okay, and you have to find the impulse delivered between the time 0 and 3 seconds. Now to do this, all you will do is you will find the area under the curve. So the area for a trapezoid is equal to nothing but the half times the base, which is 3, plus the other parallel side, or the sum of the two parallel sides, so 3 plus 1, and multiplied by the height, which happens to be 100. If you do it correctly, you will end up getting 200 newtons. So this is how you can calculate the impulse. Now if the force is given and if the time is also given, then calculating the impulse is very simple by using the F delta t equation. Okay, so now that we know impulse, let us do a quick simple derivation of the impulse momentum theorem. Now this theorem, once we derive this theorem, what you'll see some similarity between this and the work kinetic energy theorem. Okay, the work kinetic energy theorem, if you remember, said the following, that the work was equal to the change in the kinetic energy. Now the impulse momentum theorem says that the force times time is equal to pf minus pi. So this is the impulse momentum theorem. It says that the impulse is equal to the change in the momentum. Alright, so let's prove this. And what it says is the force times time is equal to change in the momentum. So first let's begin with the definition of impulse. Impulse itself is force times time. Now according to Newton's second law, force is nothing but ma. So it is ma times delta t. Now we can use this, if you remember from your 1D motion, that a times time was equal to vf minus vi. So we can use that definition and plug it in here. So we get m times vf minus vi is nothing but a times time. And now we're very close to the end. I can multiply it, I can distribute the m inside the radical, and I end up getting this. So this tells us that the impulse, which is f times delta t, is equal to mvf, and mvf is nothing but the final momentum minus the initial momentum. So this is our derivation. So now we have a very important theorem that says that the impulse is equal to the change in the momentum. So there are two ways of finding impulse. It's either force times time or the area under the curve, or it is also equal to the change in the momentum. Now this is of course a very crude way of deriving it, because here we are assuming that the force is constant, but just trust this derivation, or rather trust the result, the theorem itself, because it works in all possible cases. Okay, so that's it for this video.